Hello students, in this video we are going to solve the numericals which are asked in the university exam based on the syllabus of power system analysis. In this video actually we will try to solve the numericals which are asked in the university exam winter 2018, and also we discuss about the different patterns of the numericals which are asked in the university exam. So here we'll try to solve the numericals which are asked in the winter 2018 exam. Okay, so what is the question is, there is the numerical in question number 1b. See, this numerical is based on the syllabus complex power. We had already discussed the numericals based on the complex power, that is in few numericals there will be the number of loads, that is load 1, 2, 3 etc. are connected to the voltage source, and there will be the question about calculate the power loss or power consumed by the each load, or what is the active and reactive power consumed by the individual load, or there are the numericals in which two voltage sources are connected together through the load impedance, and we have to calculate the complex power loss in the line. So first of all we'll go through the given data for this question. What is the question? Two voltage sources V1 is equal to 130 at an angle of minus 40 degree volt and V2 is equal to 100 degree volt are connected by a line impedance of Z is equal to 2 plus J10 ohm. That is, they had given the value of voltage source V1, voltage source V2 and line impedance of Z. Determine real and reactive power loss in the line. See, in this case there is particular question about real and reactive power loss. Actually, first of all we need to calculate the total complex power loss, and then we have to segregate what is the real power loss and what is the reactive power loss. So we'll try to solve this numerical. Mostly in such type of the numerical, make the practice to draw the diagram. Actually here I didn't draw the diagram, but we can draw the diagram, that is two voltage source V1 and V2 are connected by the line impedance Z, and you can give the ratings of voltage sources and impedances which are given in the numerical. So as per the given data, here V1 is nothing but value of the voltage source 1. It is equal to 130 at an angle of minus 40 degree volt. Voltage source V2 is equal to 100 at an angle of 0 degree volt. That is, voltage values are given in polar form, and Z is equal to Z plus J0 ohm, where Z denote the impedance, the value of the impedance as line impedance in ohm, and it is given in rectangular form. Now we'll try to calculate the current which is flowing from the source 1 to 2. So here I12, here I shows the current and 12 represent that this current is flowing from source 1 to source 2. And what is the formula for this? I12 is equal to V1 minus V2 upon Z. So you are having the value of V1 130 at an angle of minus 40 degree, V2 is equal to 100 at an angle of 0 degree, and impedance Z is equal to 1 plus J7. But we are having the idea that in case of the addition and multiplication, it is done in term of the rectangular form, and for the multiplication and division there is a requirement of polar form. So here the values which are given in the rectangular form, first of all we have to do the subtraction. That's why we will use that values, that we have to use the subtraction. That's why we have to convert these polar values into the rectangular values. That is 130 at an angle of minus 4 degree, which is in polar form, can be converted into the rectangular form, which is equal to 129.68 minus j 9.06, and the value 100 at an angle of 0, that is value of V2, which is in polar form. In rectangular form, it will be equal to 100 plus j0. Now we can do the subtraction. So after subtraction, that value becomes equal to 29.68 minus j 9.06 upon polar form, that is 1 upon impedance 1 plus j7. But now we have to do the division, and we are having the idea that for doing the division, there is both the values should be in polar form. So we'll convert these rectangular values into the polar form. So it will be equivalent to 31.03 at an angle of minus 16.98 upon 7.07 at an angle of 81.87. So in polar form, it will be equal to 4.39 at an angle of minus 98.85 ampere. That is, we are having the value of current I12, which is flowing from source 1 to source 2 in term of the polar form. Now similarly, we'll calculate the value of I21. What is the meaning of I21? It is the current which is flowing from the voltage source 2 to the voltage source 1. And similar to the first case, it will be equal to V2 minus V1 upon Z. So here V2 in polar form is given. Since we have to do the subtraction, we'll convert these values into the rectangular form. So this 100 at an angle of 0 in polar form becomes equivalent to 100 plus J0 minus 130 at an angle of minus 4 in polar form, it becomes equivalent to 129.68 minus j 9.06 upon impedance 1 plus j7. So in this value, numerator value will become equal to minus 29.68 plus j 9.06 upon 1 plus j7. But we have to do the division, and that's why we will convert these values into the polar form. In polar form, it will be 31.03 at an angle of 163.02 upon 7.06 at an angle of 81.87. So I21 will be equal to 4.39 at an angle of 81.15 ampere. So now you are having the value of current which is flowing from the source 1 to source 2, that is I12, and current which is flowing from the source 2 to source 1, that is I21. Now we'll calculate the complex power which will flow from the source 1 to source 2, and it is represented by S12. Here S represent complex power and 12 represent that it is flowing from source 1 to source 2. So it will be equal to V1 into I12 star. Here V1 is the voltage and I12, that is the current flowing from source 1 to source 2. But we are having the idea that complex power is nothing but multiplication of the voltage and complex conjugate of current. So it will be multiplication of V1 into I12 star. So what is the I12, which is already calculated in step 1? I12 is equal to 4.39 at an angle of minus 98.85. But here there is a requirement of complex conjugate of current I12. So it will becomes 4.39 at an angle of plus 98.85. So don't make mistake here, otherwise your answer will be wrong. So it will be V1 into I12 star. So in polar form, it will be equal to 57.07 at an angle of 94.85, and in rectangular form, it will be equal to the minus 48.25 plus J568.66 volt ampere reactive. So we had written the calculated the complex power S12. Similarly, we'll calculate the complex power which will flow from the source 2 to the source 1 and denoted by S21, where S represent the complex power and 21 represent this complex power flows from voltage source V2 to voltage source V1. So it will be equal to V2 into I21 star, and it will be equal to V2 is already given 100 at an angle of 0 and I21 which we had calculated in step 2 equal to 4.39 at an angle of 81.15. But since we are interested in the complex conjugate of current I21, so it will be 4.39 at an angle of minus 81.15. So it will be equal to 439 at an angle of minus 81.15, and in rectangular form it will be equal to 67.53 minus J for 33.77 volt ampere reactive. That is, you had calculated the complex power going from the voltage source V2 to voltage source V1. Now you are having both complex power S12 and ST1. So line loss, that is complex power loss, which is denoted by S suffix L, where S is the complex power and L indicates line loss, is equal to addition of these two powers S12 and S21. So it will become 19.28 plus J134.89 volt ampere reactive. See, most of the students solve answer up to this step only. But what is the question? What is the required data or what is the needed answer for the question? There is a requirement of calculation of real power loss and reactive power loss. So we are having the idea that complex power is nothing but it is the combination of active power and reactive power. So first part is represent P, that is active power, and this second part represent the Q, that is reactive power. So real power loss, which is denoted by P suffix L, where P is for active power, L for line loss, PL is equal to 19.28 watt. Make sure that always you write the answer with unit, because in case of electrical engineering, any value without the unit is meaningless. So real power loss PL is equal to 19.28 watt. And reactive power loss QL, here Q is the reactive power, L indicates the line loss, so QL is equal to 134.89, and what is the unit for the reactive power? Volt ampere reactive. So we had calculated the real power loss and reactive power loss. So mostly don't make mistake while writing the answer, always write the answer with its unit. Now we'll see any other example which is asked in this exam is question number 2b. So what is the question? Actually this question is based on the syllabus of power system modeling. Till now we had discussed in case of the unit 2, that is modeling of the generator, modeling of the transformer, modeling of the transmission line, etc. And this question is based on the transformer modeling. So what is the question? A 5 kVA 400 by 200 volt 50 Hz single phase transformer has primary and secondary leakage reactance each of 2.5 ohm. That is, the transformer rating is given, it is of step down type of the transformer, frequency is given, type of the transformer is single phase transformer, and whose primary and secondary leakage reactances are given. But what is the question? Determine total reactance in per unit. Now you had already studied in unit 2 what is meant by the per unit representation. That is, what are the advantages of the per unit representation, what is its use in power system analysis, then what is the basic formula, that is actual value upon base value, how to select the base value, etc. But here actually we have to calculate the total reactance in per unit. So we'll try to solve this numerical, that is the question number 2b. So what is the given data as per the example? In exam they had given the primary and secondary leakage reactance. So here we'll denote primary leakage reactance X for reactance, and X suffix 1 denote the leakage reactance for the primary side. X1 is equal to 2.5 ohm. And X suffix 2, X2 denotes the leakage reactance on the secondary side, which is equal to same 2.5 ohm. Apart from that, they had given the 5 kV is the rating of the transformer. Then ratio of the transformer is 400 by 200 volt, which is step down type of the transformer. So here we will select the base value of the voltage on the primary side, VB1 is equal to 400 volt. Base value of the voltage on the secondary side, VB2 is equal to 200 volt. And we have to calculate the reactance in per unit. But we are having the idea that whenever we are going to deal with the per unit values, the base value we need to select, and base value of the power remains same throughout the system, whereas base value of the voltage changes as per the transformer ratio. Okay, I repeat, base value of the power remains same throughout the system, but base value of the voltage changes as per the transformer ratio. So on primary side of the transformer, if we consider the 400 volt VB1 is base value, then on the secondary side, as per the transformer ratio, it will become equal to the 200 volt. And we have to calculate the transformer reactance X in per unit. So total reactance of the transformer referred to the primary is given by X1E is equal to X1 plus X2 upon N1 by N2 bracket square. So what is the meaning of X1E? It is the 1 for primary side, E for equivalent reactance and X for reactance. That means it is equivalent reactance on the primary side of the transformer, which is denoted by X1E. And what is the formula? It is equal to X1 plus X2 into N1 by N2 bracket square, where X1 is the primary reactance on the primary side, X2 is the reactance on the secondary side, and N1 by N2 is the turn ratio, which is equal to voltage ratio of the transformer, and we have to consider the square of that value. So X1, that is 2.5, that is leakage reactance on the primary side as per the given data, plus 2.5 X2 into N1 by N2 will be equal to V1 by V2, that is because turn ratio is equal to the voltage ratio 400 by 200 bracket square. So it will be 2.5 plus 10, that is 12.5 ohm. That is, we had calculated equivalent reactance on the primary of the side of the transformer. Now base voltage on the primary side VB1 is equal to 400 volt. Now X2 is equal, X per unit is equal to, that is reactance per unit is equal to X ohm into SB upon VB2, where SB is the base value of power, VB2 is the base value of voltage. So total per unit reactance refer to the primary side X1E equivalent is equal to X1E into SB upon VB1 square. So X1E we had already calculated, it is equal to 12.5 into 5 kVA, that is in volt ampere, it will be 5000 upon VB1 square, that is voltage is 400, VB1 is 400 square. So it will be equivalent reactance on the primary side of the transformer in per unit form. Here PU represents the per unit. X1E per unit is equal to 0.390625 per unit. Okay. Thus we had calculated the equivalent reactance referred to the primary side of the transformer. Now the second part, we have to calculate the equivalent reactance referred to the secondary side of the transformer. So we will follow the same procedure. Total reactance of the transformer referred to the secondary, it will be X2E, where 2 is denotes the secondary side of the transformer, E represents the equivalent value. So equivalent reactance on the secondary side of the transformer X2E is equal to X2 plus X1 into N2 upon N1 bracket square. So X2 is 2.5 plus X1 2.5 into N2, that is N2 by N1 is similar to the V2 by V1. So it will be equal to 200 by 400 bracket square. So 3.125. We had calculated the equivalent reactance on the secondary side of the transformer. Now base voltage on the secondary side, on primary side it is 400. So as per the transformer ratio on the secondary side VB2, it will be equal to 200 volt, and total per unit reactance refer to the secondary X2E per unit is equal to X2E into SB upon VB2 bracket square, where X2E we had already calculated in step 1 3.125 into SB in volt ampere, base value of the power 5 kVA, that is 5000 volt ampere, upon VB2 base voltage on the secondary side bracket square, that is 200 square. So it will be 0.390625 per unit. See, now in this numerical, actually where in case of the per unit form, we had already discussed what are the advantages of the per unit quantity. One advantage is that per unit value remains same on primary as well as secondary side of the transformer. So here also through this numerical also we will get the idea, and those who are already having idea about this statement, they will verify their answer whether X1E per unit and X2E per unit are same or not. If it is same, that means you had solved the numerical correctly. Thus in per unit form, the reactance on the primary and secondary side of the transformer remains same. But as per the question, They had asked about the calculation of the per unit reactance on primary and secondary side. In per unit we had calculated. Okay, now we'll see the next numerical. Is there any next numerical which is asked in this same exam? Yes, the question number 3, and this is based on the syllabus of load flow analysis, and subtopic is calculation of admittance matrix. Okay, so what is the question? Now in this case, before going to solve the numerical, we are having the idea that what are the advantages of the Y bus matrix or admittance matrix, then how to calculate the diagonal and off diagonal element. Okay, of course we'll discuss in detail whenever their step will come, but right now just keep in mind that we are going to solve the numerical based on the concept of admittance matrix. So what is the question? Figure 3.1 shows the one line diagram of simple 4 bus system. So here are 4 buses are connected, that is bus number 1, bus number 2, bus number 3 and bus number 4. Then table 3.1 gives the line admittances, identify the buses on which these terminate. So this gives the line admittances. See, for the line admittance which is denoted by the Y, we are having the idea that Y is equal to G plus minus JB, where G is the conductance and B is the susceptance. So in few numericals, there might be the question they had directly given the admittance, but in few questions they will give the idea about G and B from which we have to calculate the admittance. For example, for line to 1 to 2, they had given G is equal to 2 and B is equal to minus 6, from which you will get the idea that admittance for the line 1 to 2 is nothing but 2 minus J6 per unit. Similarly, admittance for the line 1 to 3 is 1 minus J3, for 2 to 3 0.666 minus J2.0, for 2 to 4 1 minus J3, for 3 to 4 admittance is 2 minus J6. Okay, so they had given the idea about admittances. The shunt admittances at all the buses is assumed to be negligible. Okay, that is the condition for the question. And through the diagram, it is clear that bus number 1 and bus number 3 are connected. Then 2 and 3 are connected, 2 and 4 are connected, and bus 3 and 4 are connected. But this line shown, one line is shown is dotted. And what is the question? The question is divided into two subpart. First one, find the Y bus assuming that line shown dotted is not connected. That is, this dotted line is not connected. That means connection between 1 and 2 bus is absent. Okay, so and we have to find out the Y bus matrix. And what is the second part? What modification need to be carried out in Y bus if the line shown dotted is connected? That is, whenever this extra bus 1 to 2 will be connected, what modification need to be done in Y bus matrix? So we'll try to solve the numerical. First of all, we'll consider the first case in which bus number 1 and 2, that is line shown dotted, is not connected. So in case of the Y bus matrix, we are having the idea that is first you should have the idea how to decide the size of the Y bus matrix from the given data. So for what is the statement? The size of the Y bus matrix is n by n, where for n number of buses system. That is, whenever in a given system n number of buses are present, the size of the Y bus matrix is n by n. In this case, how many number of buses are connected? Bus number 1, 2, 3, 4. That means what will be the size of Y bus matrix? 4 by 4. Okay. Now that means for the case 1, whenever the line shown dotted is not connected, size of the Y bus matrix will be same, 4 by 4. So in generalized form, we'll write down the Y bus is equal to 4 by 4 matrix. That is Y11, Y12, Y13, Y14 up to the Y44. Now this Y bus matrix is divided into two parts. Diagonal element. So what are the diagonal element? We are having the idea diagonal element is nothing but YI, where I is equal to I. Okay. So here Y11, Y22, Y33 and Y44 are the diagonal element of the Y bus matrix, and remaining are off diagonal element, because we are having the idea that Yij where I is not equal to j is called as the off diagonal element. So here off diagonal element of this y bus matrix are y12, y13, y14, etc. Okay, and we are having the idea about how to calculate the diagonal element. So diagonal element, that is yi, where I is equal to I, diagonal element of the matrix is nothing but sum of, that is positive sum of all the admittances which are connected to that bus. What is the meaning of this? Y11 is the positive sum of all the admittances which are connected to the bus number 1. Similarly, Y22 is nothing but positive sum of all the admittances which are connected to the bus 2. This rule is for diagonal element only. Similarly, Y33 and Y44 are nothing but positive sum of all the admittances which are connected to the bus 3 and bus 4. So here we will try to calculate the Y11 parameter. So for Y11, that is positive sum of all the admittances which are connected to the bus 1. But from the diagram, since dotted line is not connected, only bus number 3 is connected to the bus number 1. So positive sum of admittances which are connected to the bus 1, that is y13, and from the table it is clear that y13 is nothing but 1 minus j3. Admittance y13 is nothing but 1 minus j3. So we'll write y here y13. Of course we'll put the values of actually admittances from the table afterwards, but right now I'm just writing y13. Now how to calculate the off diagonal element? Off diagonal element is nothing but negative sum of all the admittances which are connected between that buses, where Yij is nothing but off diagonal element, and which is denoted by negative sum of all the admittances which are connected between bus I and bus j. So here Y12 is nothing but negative sum of all the admittances which are connected between bus 1 and bus 2. So here in case of bus 1 and bus 2, what is the admittance? But line shown dotted is not connected. That means no any admittance will be present between bus number 1 and 2, and hence y12 will be 0. Okay, hence y12 is 0. Now how to calculate y13? Y13 is again off diagonal element. That means it is negative sum of all the admittances which are connected between bus number 1 and 3. So in between bus number 1 and 3 there is connection, and that means y13 bus will be present, but it is negative sum, so it will be minus y13 because it is off diagonal element. Similarly, y14 is nothing but negative sum of all the admittances which are connected between bus number 1 and 4, but between bus number 1 and 4 no any bus is connected, there is no directly connection, so that parameter will be 0. So it is 0. Now here we will calculate the y21. What is the meaning of y21? Y21 is nothing but negative sum of all the admittances which are connected between bus 2 and 1. But since there is no connection between bus 1 and 2, it will be 0. Apart from that, if we have to save the time during the exam, we are having the one statement or one property of the Y bus matrix. The Y bus matrix is called as the symmetric matrix because in this case Yij is equal to Yji. What is the meaning of that? The meaning of this is y12 is equal to y21 or y34 is equal to y43. So here if we consider y21 is equal to y12, see y12 and y21 are having same value. That's why Y bus matrix is called as the symmetric matrix. So you can directly write the Y bus matrix is symmetric matrix, hence y12 is equal to y21 is equal to 0, or you can calculate the value independently. Now we have to calculate the next parameter y22. Now y22 is the diagonal element or off diagonal element? It is diagonal element. We are having the rule that diagonal element is nothing but positive sum of all the admittances which are connected to the bus number 2. So to bus number 2 there are two buses are connected, bus number 3 and bus number 4. So it is the positive sum of y23 and y24. It is the positive sum of y23 and y24. So it will be y23 plus y24. Now y23 is negative sorry, off diagonal element. So it is the negative sum of all the admittances which are connected to the bus number 2 and 3. Since bus number 2 and 3 are connected, that's why we'll write minus y23. Again y24 is the off diagonal element, and since it is negative sum of all the elements which are connected to the bus number 2 and 4, but bus number 2 and 4 are connected, that means it will be minus y24. Okay, again y31 is the off diagonal element, means negative value, but it is the negative value of admittance which are connected between bus number 1 and 3. So y31, bus number 3 and 1 are connected, so it will be minus y13. Now y32 is nothing but negative sum of all the admittances which are connected between bus 3 and 2. So it will be minus, and between bus 2 and 3 there is connection, that's why it will be minus y23. Now y33 is the diagonal element. Diagonal element means it is positive sum of all the admittances which are connected to the bus number 3. So to bus number 3 which buses are connected, bus number 1, 2 and 4. All three buses are connected to the bus number 3. So it will be positive sum of y31 plus y32 plus y34. And y34 is the off diagonal element. That means it is negative sum of all the admittances which are connected between bus number 3 and 4. So in bus number 3 and 4, bus number 3 and 4, there is connection. That's why it will be minus y34. Similarly, y41 is the off diagonal element. It is the negative sum of admittances connected between bus number 4 and 1. But there is no connection between bus number 1 and 4. So it will be 0. Then y42 is nothing but negative sum of all the admittances which are connected between bus number 2 and 4. So connection is present. That's why it will be minus y24. Just a minute. Yes. Sorry for a disturbance. Yeah. So we had calculated up to this point. We had calculated the y41, no connection, that's why it will be 0. Then y42 connection is present, since it is diagonal element, that's why, sorry, it is of diagonal element, that's why it will be minus y24. Then y3, sorry, y43, it is again of diagonal element, connection is present, that's why it will be minus y43. And y44 is nothing but positive sum of all the admittances which are connected to the bus number 4. So to the bus number 4, bus number 3 and 2 are connected. That's why it will be positive sum of y43 plus y42. Now you are having the admittance values from the table. We had already discussed how to calculate the admittance values from the table. Y is equal to G plus minus JB. So y12 is nothing but 2 minus J6, y13 is nothing but 1 minus J3, y23 is nothing but 0.666 minus J2, y24 is nothing but 1 minus J3, y34 is equal to 2 minus J6. So you have to just put all the values here, and from that you will get the y11 is equal to 1 minus J3, y12 0, y13 minus 1 plus J3, y14 0. Similarly, you can put the values and you will get the y bus matrix for the first condition, that when lines shown dotted are not connected together. Okay, that is, you will get the total y bus matrix, but make sure that this y bus matrix of should be of size n by n, where n is nothing but number of buses. Since here 4 number of buses are present, that's why size of the y bus matrix is 4 by 4 matrix. Now What is the second part? In this second case, what modification need to be carried out in Y bus if the line shown is dotted? Now here you have to calculate the Y bus matrix again whenever the extra bus is added. Now here you can solve the example in two ways. First of all, first method is that similar to the case 1, just consider this connection y12 and solve the numerical from start. That is, write the size of the y bus matrix 4 by 4, then calculate the diagonal and off diagonal element. So y11, y12, y13. So only the remaining parameters will be same, but because of the addition of this, only 4 parameters will be changed. That is y11. In case of the y11, this y12 will be added. Then in calculation of y12, instead of in last case y12 is 0. See, because there was not connection. But in this case it will be become minus y12. That is y11 will change, y12 will change, then y21 will change. Y21 will be y equal to y12, and in case of y22, apart from y24 and y23, we have to add this y21 also. That means whenever bus number 1 and 2 are line between bus and 1 and 2 is connected, then diagonal and off diagonal element of the bus number 1 and 2 will be connected, will be get changed or will be get affected. So here 4 parameters will be get affected: y11, y12, y21 and y22. Remaining all the 4 parameters will be similar to the first case, and we will get the new y bus matrix. And apart from that, there is one rule from which also you can solve. So we'll see that rule. What is the rule? If any new line is added at that time, diagonal and off diagonal element of that bus 1 will be get affected. So how the diagonal and off diagonal element get affected? The diagonal element will get affected by addition of positive or addition of the newly added admittance in that bus. That means y11, which is the diagonal element, will be nothing but addition of newly added admittance. So what is the newly added admittance? 2 minus j6. Because if we go through the diagram, right now we are adding the y12. So what is the value of y12? 2 minus j6. So this newly added y bus admittance will be added in the original or old one diagonal element. Whereas new admittance will be subtracted in case of the off diagonal element. So in this case, off diagonal element, suppose y12 new, then the newly added admittance will be get subtracted from this old one. So y12 old minus 2 minus j6. So it will be, just keep in mind that in this case, because of the additional line between bus number 1 and 2, y11, y12, y21 and y22 will be get affected. So first of all, we'll calculate y11 new. That means after addition of line between bus number 1 and 2, y11 new is equal to y11 old plus 2 minus j6. So what is the y11 old? One from the case 1 minus j3 plus 2 minus j6. It will be 3 minus j9. That means what will be the modification? This 1 minus j3 in last y bus matrix will be get replaced by 3 minus j9. What is the second parameter which will be affected? y12. So y12, which is the off diagonal element, that means newly added admittance will be get subtracted from it. So it will be y12 old minus 2 minus j6. So what is the y12 old? 0. So 0 minus 2 minus j6, that is minus 2 plus j6, which is equal to y21 new, because we are having the idea that y bus matrix is the symmetric matrix in which y12 is equal to y21. Now y22 new is equal to y22 old plus 2 minus j6. So y22 new, what is the y22 old? Old value of the y22, 1.666 minus j5 plus 2 minus j6. So it will be 3.666 minus j11. So this modified Y bus will be here, value of these parameters will be get changed and will get this new Y bus matrix. So these are the modification when line shown dotted is connected. Of course, you have to practice more numericals to get the confidence about the numericals based on the syllabus of formation of Y bus matrix. Now, is there any other example which is asked in the same university exam? Is question number 4, and it is based on the syllabus of symmetrical fault analysis. It is based on the syllabus symmetrical fault analysis. So what is the question? A 3-phase 5 MVA 6.6 kV alternator with a reactance of 8% is connected to feeder of series impedance 0.12 plus J 0.48 ohm per phase per kilometer. That is rating of the alternator, its reactance, and the rating of the impedance through which it is connected are given. The transformer is rated at 3 MVA 6.6 kV by 33 kV and has a reactance of 5%. That is reactance. Details of the transformer are also given. That is transformer is of step up type of the transformer, and leakage reactance and power rating values is also given. Determine the fault current supplied by the generator operating under no load with a voltage of 6.9 kV when 3-phase symmetrical fault occur at the point 15 km along the feeder. That is length of the feeder is given 15 km, voltage is given 6.9 kV, but 3-phase symmetrical fault, that is according to the type of fault you should get the idea whether it is the example of symmetrical fault analysis or unsymmetrical fault analysis, and then accordingly you have to consider the assumption for the symmetrical and unsymmetrical fault analysis. So in this case, it is the example of the symmetrical fault analysis, and what actually we have to calculate, you have to calculate the fault current, that is short circuit current, whenever the symmetrical fault occur at the 15 km along the feeder. So we'll try to solve this numerical. This numerical is actually question number 4. So first of all, we consider the base power value. So actually, as per the given data, they had given the transformer rating 5 MVA. We'll consider the same as base value of the power. See, you can select the base value of the power, either the maximum power value or in multiple of the 100, and accordingly your base value of the voltage will change. But your base value or base value of the voltage or current will not affect the final value, because of course your per unit value may change, but when you will convert that per unit value into the actual value, that value will be same. So you can consider the base value of power. Here we will consider the transformer rating, that is as base value. So base value of the power, let base kVA for complete circuit will be 5000 kVA. Base kV will be 6.6 kV for generator side and 33 kV for the feeder side, because there is transformer which is having 6.6 kV by 33 kV, and we are having the idea that base value of the power remains same throughout the system, but base value of the voltage will change as per the transformer ratio. So here on the primary side, that is on generator side, base value of the voltage is 6.6 kV, and on secondary side, that is on feeder side, it will be 33 kV. Now per unit reactance of the alternator, they had given 8%, that is 8 by 100 is equal to 0.0 per unit, and per unit reactance of the transformer is, they had given the reactance of the transformer is 5%, but as per the new base value we have to use the change of base formula. So 5 by 100 into new base value of power upon old base value of power. So what is the new base value of the power? 5000, and for transformer old base value of the power is 3000. So it will be 0.0833 per unit. So now you are having the per unit reactance of the alternator, per unit reactance of the transformer. Now impedance of the feeder of length 15 km, ZF is equal to, actually this value of impedance is given ohm per phase per kilometer. To calculate the total impedance value, we have to multiply it by the length in kilometer. So it will be 15 into 15 is the length in kilometer into 0.12 plus j 0.48, which is the impedance of the transmission line. So it will be total impedance will be 1 point plus j 7.2 ohm, and in polar form it will be 7.42 at an angle of 36 degree, sorry 76 degree ohm. So you are having the impedance value in ohm. Now we will calculate per unit reactance of the feeder. So ZF per unit is equal to actual impedance into kVA base upon kV base bracket square into 1000. So why this 1000? Because actually formula is MVA base upon kV base bracket square. Since we have considered kV base, that's why it is divided by 1000. So what is the actual value? We had calculated here 7.40 at an angle of 76 degree in ohm into base value of power 5000 upon base voltage value bracket square, that is 33 square into 1000. So you will get the 0.034 per unit at an angle of 76 degree, or in rectangular form it will be 0.088 for 0.08 plus j 0.033 per unit. So now you are having the reactance of the feeder in per unit form. Now total per unit impedance up to the fault point Z equivalent per unit is equal to addition of all these reactances. So reactance of the alternator, that is 0.08 plus j 0.0833, that is reactance of the transformer, plus reactance of the feeder reactance, that is 0.08 plus j 0.033 per unit. So it will be equal to j 0.008 plus j 0.196 in rectangular form, and in polar form it is 0.196 at an angle of 87.66 degree per unit. Now base value of the current. We are having the idea that if you are having the idea about base value of the power, base value of the voltage, you can calculate the any other base values. So base value of the current I suffix B, here B is denote the base value. So base value of the current IB is equal to base kVA upon root 3 into base kV. So base kV is 5000 upon root 3 into base kV is 33. So 87 by 4, 87,477 ampere is the base current. Now if we have to draw the same structure through the diagram, this is the reactance of generator rating, that is 6.6 5 MVA 6.6 kV, and reactance is 0.08. This is the transformer 3 MVA 6.6 kV by 33 kV, reactance in per unit is J 0.05 per unit. Then this is the feeder, the reactance is 18 plus J 7.2 ohm, and this is the fault point at 15 km from the line. So this is the one line diagram. Now once you are having the one line diagram, you are having the all the values in per unit values, so you can calculate the draw the reactance diagram. So in case of the reactance diagram, we are having the idea that generator in terms of the reactance form, it will be EMF behind transient reactance. So this is E and EMF, then reactance of the generator, then reactance of the transformer, then reactance of the feeder, and this is the fault point. So we have to calculate actually the symmetrical short circuit current, that is fault current. So fault current ISC is equal to ISC per unit. So what is the ISC per unit actually? Fault voltage divided by fault impedance. So you will get the voltage divided by fault impedance, that is short circuit current per unit. It will be equal to 5.3285 at an angle of minus 87.66. So how it is calculated? Here actually this short circuit current per unit is nothing but P upon ZF. But in case of the symmetrical fault analysis, we consider the generator EMP equal to 1. So it will be 1 upon Z per unit. So 1 upon 0.1962 at an angle of 87.66, it will be 5.3285 at an angle of minus 87.6. So this short circuit current per unit, if we multiply it by base value, because we are having the idea that actual value is nothing but per unit value into base value. So this is per unit value into base value is 87.477. So it will be 466 Here actually this current is 87.477. So this current is 466 at an angle of minus 87.66 ampere. Thus we had calculated the fault current. So what is the steps we had followed? First of all, we had converted all the reactances and impedances in per unit form. Then from which we draw the single line diagram. Single line diagram is converted into the reactance diagram, and from the reactance diagram we had calculated the short circuit current, and then by using the base value we had converted the per unit value into the actual value. Okay. Of course, you have to practice more and more numericals. Now, this is the last question which is asked in this university exam. It is question number 5B, and of course, it is related to the based on syllabus of unsymmetrical fault analysis. So, you are already having the idea what are the example of the unsymmetrical fault analysis, from which also you can get the idea whether it is the example of symmetrical fault analysis or unsymmetrical fault analysis. So, quickly we'll go through the given data. What is the given data? A 10 MV 13.8 kV alternator has positive, negative and zero sequence reactance of 30%, 40% and 5% respectively. That is, positive, negative and zero sequence reactances are given in terms of the percentage. What reactance must be put in the generator neutral so that the fault current for line to ground fault of zero fault impedance will not exceed the rated line current, and to express the reactance both in per unit and in ohms. I think few students may get idea from the given data only. Here we have to calculate the reactance which will be put in the generator neutral to limit the fault current, and we are having the idea that this reactance is nothing but current limiting reactor. So what are the specification of current limiting reactor? How to select the current limiting reactor? That point we had already covered in the unsymmetrical fault analysis unit. Here what we have to do? We have to calculate the value of that reactance for the given specification of generator and positive, negative and zero sequence reactances to limit the fault current and up to the rated line current. And you have to calculate that reactance both in per unit and in ohm value. So we'll try to solve this numerical. Actually, this numerical is based on the concept of selection of current limiting reactor. So let base MVA be 10. That is, we consider the power will be 10 MVA. Then base voltage is 13.8, which is the voltage of the generator only. That is, power rating and voltage rating of the alternator will consider as the base value of power and base value of voltage. So base value of the power is 10 MVA, base value of the voltage is 13.8 kV, and we are having the one assumption. In case of the unsymmetrical fault analysis, we will consider always EMF equal to the 1 per unit. So here we will consider EA is equal to 1 plus J0 per unit. Now base impedance is equal to, we are having the basic formula, base impedance is equal to base kV bracket square upon base MV. I repeat, we are having the basic formula, base impedance is equal to base kV square upon base MV. So what is the base kV in this case? 13.8 bracket square upon 10, that is 19.044 ohm. So this is the base value of impedance. Always keep in mind that you can select the base value of power, base value of the voltage as per your assumption, but base value of the power remains same throughout the system in case of the per unit form, whereas base value of the voltage changes as per the transformer ratio. And according to, if we are having the idea about the base value of power, we are having the idea about the base value of voltage, you can calculate any other base value like base value of the current, base value of the impedance, base value of the reactance, etc. So in this case, actually we need to calculate the base impedance. So we are having the basic formula, base kV square upon base MVA, that is 13.8 square upon 10, will get the base value of the impedance in 19.044 ohm. Now we have to calculate the fault current. What is the fault current formula? If you are having the idea about positive, negative and zero sequence reactance, fault impedance IF is equal to 3EA, where EA is nothing but armature EMF, and upon Z1 plus Z2 plus Z0 plus 3Zn plus 3Zf. where Z1, Z2 and Z0 are nothing but positive, negative and zero sequence impedance. Zn is nothing but impedance of the neutral, and Zf is nothing but impedance up to the fault point. Okay. So what is the actual question? We have to calculate the zero fault impedance for a line to ground fault of zero fault impedance. So zero fault impedance, that means Zf will be 0. Then we have to calculate up to the current fault impedance will not exceed the rated line current. So here you are having idea about the other remaining parameters, but we have to calculate the impedance of the neutral. That reactance actually we have to calculate, because we are in this case we are going to consider the current limiting reactance. That's why resistance will be 0. That's why this Zn will be replaced by Xn in succeeding formula. So 3 into EMP is 1 as per the assumption for unsymmetrical fault analysis upon J. Z1 positive sequence impedance 0.3, Z2 negative sequence impedance 0.4, then Z0 0 sequence impedance 0.05 plus 3 Xn we have to calculate, plus Zf is 0, hence 3 Zf will be 0. So we will get the Xn in term of per unit 0.75. So now you are calculated that reactance in per unit form. But to convert it into the actual form, you should have the idea about the base value, because we are having the idea that actual value is nothing but per unit value into the base value. So Xn is equal to base impedance in per unit reactance. So base impedance is 19.044 ohm into per unit reactance 0.75. So it will be 14.283 ohm. Thus we had calculated that reactance both in per unit form and both in per unit form and in actual ohm. Thus we had solved this numerical. See, so through this video lecture, actually we had seen the different type of the numerical which are asked in the university exam. Of course, you have to practice more and more numericals so that you will get the idea about variety of the numericals. So what will be the change parameters, and accordingly, if you practice more, then the mistakes during the final university exam will be avoided. Because, and always keep in mind that regarding the numerical, you should have the idea about the basic values. Whenever you are going to solve the numerical, first of all write down the given data, then what is the required data, and if there is any assumption, then what is the basic formula, that write down, and then if possible try to draw the diagram as per the given data, and then only try to solve the answer numericals. Okay, so with this we are going to end this video session. Thank you.